In this problem, a rock of mass 0.03 kilograms is thrown upward with an initial speed of 17 meters per second. Can you find the work done by gravity on the rock from the time it leaves the thrower's hand until it reaches the highest point on the trajectory? Okay, so once again, since this situation involves only the force of gravity on the ball, that downward force, we're not going to consider the throw, for example. This is going to be another case of conservative work being done. So when that happens here, we're going to just basically get rid of this term. It's not needed because it's 0. So what's the initial kinetic energy that the ball has? Let's find that. 1/2 mvi squared. It's going to be 1/2 0.03 kilograms, 17 meters per second squared. .335 joules. All right, that shows us how much initial kinetic energy the ball goes up with after it was thrown. How much gravitational potential energy does it have? Well, we typically make the ground 0. So let's let that be 0. What about at the peak? Is the ball moving? No, right? So that makes the final kinetic energy 0. So then it's quite easy to find out that we could solve for the UG here. The final UG will actually be 4.335 joules. It's the only way the equation could be true. So if you let the UG at the end equal 4.335 joules, then you could set that equal to mgh. And then solve for the height that the object will actually go. So it'll be 4.335 equals 0.03 times 9.8 times h. And if you just solve, you'll get a height of 14.7 meters. It's interesting because here you don't have to analyze motion in order to solve this type of problem. Like where in the past, in the first part of this investigation here into physics, we would have used kinematics, which is motion equations, to figure this out. But now we can actually use energy concerns to find that the peak is 14.7 meters. And the next one says you're going to push a refrigerator across the floor of your kitchen. You exert a force of 315 newtons for 6.9 seconds, and the refrigerator moves 2.8 meters at constant velocity. Okay, so where do we start? Let's see. The fridge is on level ground. So what's the gravitational potential energy at now? It's 0, right? And then what's it at the end? Still 0. So that makes this kind of easy here. Easier. Now let's figure out the kinetic energy the fridge has. To do that, you need the formula 1/2 mv squared. So we'll need 1/2. We need the mass of the fridge. It's a 1,000 Newton fridge, so that's actually 102 kilograms. And they said its speed is 0.1. All right, let's calculate that and get the kinetic energy at the beginning here. It's got 0.51 joules. How much kinetic energy would it have at the end? Well, use the formula 1/2 mv squared, but this time you use the final velocity, whereas we had used the initial velocity the first time. But look at that, it's constant velocity. So it's actually the same calculation. And that's how you want to do these. Like, you want to figure them out one formula at a time, fill out how much energy there is of each kind, and then we can deduce what the work must be here. It should be clear from the formula that the non-conservative work is actually 0. Now, how can that be? How could it be that the person actually pushes with a normal force, which we said was non-conservative? They push all the way across the floor. How could the net work on the fridge be 0? It's because the person puts energy into the box by pushing, but at the same time, that energy is leaving the box through friction. And so it results in no net work being done. There's positive work being done by the person's push. But it's negative work when friction takes energy out of the system, see? And friction's going to take out just as much as the person pushes in. We know that because the fridge is at constant velocity. So it must be that the reason that the fridge's velocity isn't changing, its speed's not increasing, is because the works are balanced. All right, let's check out this one, though. It says a car of mass 1,600 kilograms is initially traveling with a speed of 20 meters per second, but then the driver accelerates to a speed of 35 meters per second. And it takes a distance of 400 meters to do that. Calculate the energy that was added to the car. So that right there, that last sentence tells us that there is going to be a net work done from outside the system in this situation. So where does that work come from? From the engine of the car. Okay, so let's put down the formulas. 1/2 mvi squared plus mgh plus work equals 1/2 mv final squared plus mgh, and keep in mind that's the initial height of the car. That's the final height. And this is a car just on a level road, we assume. So the gravitational potential at the start is 0, and the gravitational potential at the end is 0 too. It's all based on height and mass and g. So now let's find the kinetic energy that it had at the start. Okay, that's going to be 1/2 1,600 20 squared. Okay, how much kinetic energy did it have at the end? 1/2 1,600 35 squared. So see, something had to make that energy go up, that kinetic energy. Let's see how much it rose. Okay, we got 320,000 joules at the start. We got 980,000 at the end. If you go ahead and subtract, we'll see that the energy put in by the engine here was 660,000 joules. So that's the point, is it requires energy from outside the system to increase the speed. So what's the system here? The frame of the car, the person who's riding in it, all that. And we want to accelerate all those things. So it takes work from the engine to do it.